think science, and I knew I was relatively good at science. So then I thought, okay, I could apply myself that way. In what ways could I apply myself? Then I studied a little bit more about engineering and what that could mean. And then I realized that engineering might be a fit for me. Now, I'll admit that I did not know much about what engineers did at the time. I knew they were involved in science. I knew they were involved in applying science to things. But then as I got into engineering, I realized how much more important engineers were for society in general. But I also realized how important the people that you are, you people, individuals sitting in the chair right now, who take ideas from a brain like mine that we collaborate on. I'm going to be looking to you people in the future here to go and tell me why my ideas were wrong, one, or two, how they could be improved. So that could be as simple as you guys being familiar with anything from a drawing or a pipe set of drawings, P&IDs, process and instrumentation diagrams, anything like that, saying, hey, you know what, Darce? I was looking at your diagram the other day, and when the door opens here, it's going to hit this valve. You didn't think about that when you were putting it together in your little map there, but I'm your boots on the ground. I'm your eyes and ears. I'm the person that's doing that extra layer of thinking that we want to see in society to go and make for better society in general. So I look to you guys as partners in all of this to make this happen. And I'll tell you that there's not one thing I've done in my career, any way, shape, or form, whether that be putting a pump in, pumping fluid, that hasn't been a collaboration of ideas with people like yourselves, other people that we rely on, let's say our instrumentation techs and whatnot. You guys are going to school with a bunch of those people that are doing E&I stuff. This all comes into play. And all of these things help make the picture full for what we need to see to go and make these decisions, whether it be engineering, whether it be design, whether it be manufacturing in terms of manufacturing a good that you want to be repeatable, sorry. If you want repeatability in life, you need to be doing things thoughtfully. You have to have thought it out, look for all the potential ways things could go wrong, and then try to solve that. And then what I like to do is take all of this math and all of these crazy equations and whatnot that you can think, and I like to try to make them practical. Because practicality is what you see around you all the time in the physical world. For example, you know gravity's keeping you in your chair. I don't need to tell you it's 9.81 meters per second squared times your mass keeping you on the chair. You know that's a physical reality. Being able to calculate that and understand what you're doing is definitely a concept that's going to lead into more understanding of future concepts, but that all builds on small understandings and diving deep into what you need to learn. So I have found that one good way of learning is through trial and error. We all know that. Burn yourself by touching the stove. However, another good way to learn is by using this thousands and thousands of examples we now have at our fingertips to learn. I think you might know Mike plays music with me, and maybe not, but we all play music together. The amount of music you can learn now on the internet is absolutely astounding, and the rate at which you can learn it is unbelievable. So a couple things I want to encourage you guys to do before we get into any of the technical today is take the opportunity to dive into some of these concepts on YouTube or any of the other channels. You can type, as an example, we're going to be talking a little bit about velocity, pipe friction, and turbulence today, and those concepts combined to kind of give you a better holistic idea of what we're trying to achieve when you're getting to think about these concepts. But by doing that, you can, to better learn about that, you can go down a ton of different rabbit holes. But one is the YouTube rabbit hole. One of them is, because YouTube is so great at doing visuals, right? Like whether it be showing a piece of pipe with flow going through it and showing concepts of pipelines shrinking and velocities increasing as pipelines shrink and volumes stay the same. But some of these concepts that I think are really best visualized with some extra ammo in the background, and maybe somebody giving you a narrative that you can pause and hit rewind on so you can watch it over and over again. And I'm now going to move into a little bit more about my experience. So when I started in my engineering world, I came out west from the Maritimes. I started working in the oil and gas fields in southern Alberta. It was shallow gas at the time and oil, conventional oil, unlike the gas I produce now, which is gas obtained through fracturing in really tight rock. We're not going to get into any of that, but throughout my career, one thing that has never been steady and stable is a path forward. It kind of has always branched off into different ways. So I didn't think I'd necessarily be doing what I'm doing today, but now I'm there. And I know I'm there because I kept learning more and more about, hey, what does the guy down the hall from me do? When he's putting two pieces of pipe together, what's actually happening there? Is he bolting them up with flanges? Is he welding them together? Is he, how are these things? Is it threaded? All of these different concepts come into play, and then you can get an appreciation for, well, what is the difference between a threaded piece of pipe and a flanged piece of pipe? Why would I want to weld something versus flange it up? You know, and then I often think about things like, you know, my wife always gives me the gears for this, but I don't like built-ins. I don't like a built-in screen, because, you know, technology changes over time. It's like building a speaker into your ceiling, which seems stupid now when you can just set a Sonos speaker anywhere in your house and it doesn't need a wire, it doesn't need cables, there's nothing running all over your floor. So, you know, those kind of things, like all this big holistic vision about how to make things better, is kind of where I'm coming at you guys today. It's like, how do you make your careers better? How do you make your learning journey better? And that is something that I think, I honestly think we fail at that in school. Like, nobody has inspired me to want to learn along the way. I don't even know why I like learning, but I do really love learning now. And I think with the right person trying to spin that around for you and giving you an appreciation for like how it works. And I know that sounds silly to say the OS word there and throw it in there, but it's true. It's like, how do things work? You know, what does a rotating shaft mean? How does that transmit energy into gears? So sorry, we're getting a little off track from where we want to go today, but I just wanted to give you guys an idea that your path forward in your careers is probably not going to be straight. It's going to branch out. So everything you can do while you're working on a job site, use those opportunities to learn about how the garbage gets taken out. I know that sounds silly, but it will give you a better perspective about how things work in the world and how what you do matters to a guy like me and to everybody else in society to make the world a better place. And I want to emphasize this a little, because again, Mike and I know a whole vast array of people, whether it be musicians, engineers, scientists, doctors, everything. And I'm talking like doctors of physics and also the medical doctors. But one thing I see common in everyone that I think has a passion for life is that willingness to learn and not, you know, maybe not want to take that easy road. The easy road is never the road that's going to get you somewhere better. And it doesn't come without strife. I can tell you, when I was in engineering school, I would sit down some nights at 6 o'clock and not end my studies till midnight. And I would look at my watch and think, there's no way that that much time could have passed. But that's what it took to go and get some of these concepts in my head. So I don't want to make you guys go down the road of making it hard. Let's try to make it easy. So with that, let's jump into some of the stuff that we want to talk to today about fluid flow in pipe and how that relates to both the friction factors and how some of those turbulent factors of the fluid flow can come into play and cause things like pressure reductions and or pressure back out in your pipe. So, and let me go into where Mike kind of came to me yesterday with the problem that we started talking about. And I think the way it was framed, and correct me if I'm wrong here, Mike, but so the idea of pipeline diameter increasing, or circumferential area, or not circumferential area, circumferential distance, i.e. the circumference of the circle, as that circle gets bigger, how do the relationships between the circle, the actual diameter of it, and the circumference change with respect to the area? So that's a concept that's kind of interesting, because as you can imagine, as the pipe gets bigger, there is more pipe wall. Therefore, there's more, if you want to think of it in terms of, there's more potential for friction. But at the same time, and this is a concept I'm going to show visually in 2 seconds when I bring up a SAIT here I'll share, at the same time, that area of the pipe is getting much bigger too. And the relationship to which the circumferential distance and the area are changing by two different magnitudes. One's changing linearly, i.e. it's being multiplied by a number like 2, and that just continues on. The other is being squared. So let me bring a little sheet up here, and I want to kind of show you guys what I'm talking about there, or what I'm, oh, Mike, you have to enable me to share here.
On it.
Yep. So one of the things that engineers love doing, just to kind of frame where I'm going with this next diagram, is like, we like to try to I always call it normalizing things. So you know, if I'm going to try to assess, and I'm going to use the apple and oranges example here, if I'm going to try to assess apples and weigh them out the oranges, like what properties of these two things do I have that are common? And, you know, one way to do that might be like, well, I'm going to sell you an apple, I'm going to sell you an orange, I'm going to sell you based on the weight, because that's something that those two properties have in common. Totally different fruits, but they have a weight I can measure. Therefore, a pound of apples costs you this much, a pound of oranges costs you this much. So where I'm going with that is I want to show you how, as I share the screen. So this is I think you guys can all see my Excel sheet now here. So what I did here, guys, is I wanted to just show you a fictional piece of pipe here. I have my pipe, the circumference being that blue dark line around the edge of the area of the circle, the diameter being this line, which indicates the basically width of that pipe on the cross-sectional area, and then the radius. And what I really want to show here is how the pipe size, and I just used inches in here. That could have been meters, that could have been centimeters, that could have been millimeters. I'm sure Mike and the rest of the SAIT folks have emphasized how important it is to have units of the same measure, i.e. when you're working with inches, you got to be working in inches. If you're working in millimeters or thousandths of an inch, you work in the same units all the time. That's just important for relativity. But as you can see here, let's look at how the circumference of the circle that we're creating within that pipe, let's look at how the ratio of the circumference changes with respect to the area. So let's look at how this blue distance all around here, if you can see my mouse going around, changes with respect to the shaded blue area here. And as you can see, when I go from 2-inch pipe to 4-inch pipe, my circumferential distance, so to speak, goes from 6.3 inches up to 12.6 inches, which is 100% increase in distance. At that same time, the cross-sectional area went from 3.1 inches squared to 12.6 inches squared, which is a 300% increase in area. So that is a concept that I want you guys to get in your heads, because yes, there's more potential for friction, but there's also a whole lot more space in there with respect to that potential for friction for less friction. And that matters when you're thinking about the way fluids move through a pipe. And this is where I want to get down to the easy to understand conceptual thing we're talking about here. Okay, and I think that's best described with a quick view of, just one sec here, gang. I just want to minimize this a little bit. Move this down. This was sorry, I have a picture here I want to show you guys. This picture, if you can see, is a picture of flow through pipe. And what the diagram is trying to represent, it's trying to represent a few things here. It's trying to show you that as you move away from the pipe wall, the velocity of the fluids moving through the pipe, assuming the pipe is full of fluid, like there's no space, there's no water sitting halfway in a pipe, there's no space, it's full of fluid. As that fluid's moving, the velocity in the actual pipeline itself, the velocities change as you go through that cross-sectional area of the pipe. And essentially all it's saying is that in the middle of the pipe, there's the least amount of turbulence effects and friction effects to hold back or push back on what you're trying to achieve, which is fluid flow through that pipe. And I think this diagram here, when you're showing turbulence, gives you an idea of what's happening at kind of more molecular or a fluid level within the pipe to go and cause more back pressure and or add to the pressure that's pushing back on what you're trying to achieve. And I always like to think of it this way. Think of a garden hose versus a 3-inch PVC pipe. The 3-inch PVC pipe has a ton of room. If you got water shooting out that's equivalent to a hose volume, it's gonna be trickling out of there. That hose would be full of that volume, and the friction in the hose would be a hell of a lot bigger than what you'd see in that PVC pipe, just based on the fact that there's more area. But now we get into the concept, and this is where I want to try to make it easy for you guys. Most of you, I assume, have stood by a stream at some point in time in your lives. A stream is a great analog or a great comparison to think of when you're thinking about flow down a pipeline. Closer to the edges of the stream, you can actually get places where you get eddies and the stream is flowing back on itself. That is exactly like the pipe wall we're talking about. The pipe wall on a molecular scale is jagged. There's like edges on that pipe that you can't see. You can't even feel them just because our skin and stuff don't get in there. So imagine a big rock on the side of a river, and just ahead of that rock, the fluid's coming, like your river's flowing at it, and it hits that rock and it starts swirling around. Eventually that fluid does move around the rock, but the rock has an effect in the way that that fluid has to move past it. That is exactly what's happening inside the pipe and on the pipe wall. Now imagine that rock in the stream has created this big eddy. The eddy is actually pushing also out into the main form of the stream. So it is affecting the full flow of the way the river moves. And I mean, like, I don't want to get into the whole erosional side of things too, but that is changing the dynamic of how the fluid's moving in the stream. And it will change things like the velocity in the actual river stream. And that there, again, it's the exact same concept. So if we think about, okay, what is going to add to friction in a pipe? That is where we get into the actual equations that we're talking with. And I know Mike has probably talked to you guys about head loss and calculating head, like what potential energy is in a column of fluid, how much pressure can a column of fluid exert. That's how much work it can do at any given point in time. And these equations, if we go back to what I was talking about with respect to pipe area and circumferential distance changing with respect to each other, all of these things are interrelated in terms of, oh, sorry, I'm on the wrong screen here, guys. How this friction factor here, or the head we calculate as loss, is affected by this D parameter here in the equation. So if you can imagine that, okay, pipelines are flowing, there's friction throughout the whole pipeline, assuming it's full of fluid, there's contact on those pipe walls that's pushing back. As the velocity increases through that system, two things are going to increase. The friction, one, is going to increase, and the turbulence is going to increase. The friction factor will increase and therefore cause you to have to push harder to achieve the same work at the end of the pipe. And that turbulence factor is going to come into play too. Now imagine all those little eddies on the edge of the pipeline pushing back on the next piece of fluid that's coming into it. And those processes, those physical processes, are very dynamic, and they happen within that pipeline, and it all equates to pressure loss or head loss. So if you can simplistically think about it that way, that to me is the best analog to go and visualize what's happening within these pipes. Now, another component that comes into play here, as you guys can imagine, again, I like to make this as simple as I can, is the idea of viscosity within these fluids. So you can imagine pumping water is a lot different than pumping honey. Honey is much more viscous. It's bound together more. It's harder to push. And that's where the differences in fluid dynamics come into play in relation to all of these frictional factors that we're talking about. But again, those same concepts have to come into play, where you look at the pipe diameter size, like how much physical area do you have to flow with, versus that circumferential area or circumferential distance, and how much contact that would have with the fluid. And if you understand how those relationships change as the pipeline size gets bigger, then you get a good concept of how those friction and turbulence factors will change as well. So that being said, I can understand how some of that might be a little confusing for you guys, or it might be a little bit of a different concept to grasp, because I think, and I'll go back to that conversation you guys were having with Mike, we could imagine that the physical amount of potential contact on a pipe that gets bigger is you have more pipe area to contact, or more pipe surface to contact. Therefore, there's more, like I said, there's more potential for friction. The friction factor, though, is not the dominant one with respect to how that area is changing. So the fact that that area is changing much bigger gives you more area or more space for things to operate in a less turbulent and a less friction affected environment. So does that concept does that help frame it a little better for you guys, or what? Somebody give me a question here. Who's got a question as to what I've said? Is there anything that's maybe a little unclear there? What kind of clarity can I provide there to help with that concept? Any question is good too, guys. There's no dumb questions.
Anybody? No. So you 12-inch pipe. We got water flowing through there. Obviously, there's friction loss on the outside, but you're saying there's more turbulent flow down through the center. Got to push it towards the middle. What happens when you hit a 90-degree elbow or something? There's more volume, more weight. How do you get that?
That's a great question. So imagine this. So you're envisioning this pipe elbow, right? And I think, so here, I'm doing my best vision of a 90-degree pipe elbow. You have that flow coming in there. And what you're describing now is an actual physical change in the direction of flow. So then you might ask yourself, okay, what does that elbow introduce as a friction in my system? Because now you've changed the flow. You've added turbulence to that point of the system in which the flow is then going to have to bend and move around. So you can imagine, just picture one molecule of water flowing down that pipe. It comes in here, it hits the edge of that elbow where you're trying to direct the flight. So it hits there, it bounces back, and it runs into the next piece of fluid that's coming in. Those energies that are being balanced there as those two molecules come in together, that is your loss. That's the loss of energy in your system. It's like heat in an engine. You're losing heat out of the engine that could have been used to do some work for you, but you can't capture it. So that elbow, and this is why that concept is great. You can have the same physical area in that elbow, right? As you go across, you have the same cross-sectional area, but the turbulence, your Reynolds number, has increased there. So it's not so much friction, it's turbulence that you've created within that elbow that pushes back on the work you're trying to do. Does that make sense?
Yeah.
So and another way to look at it is like think about the end of your hose, okay? The end of your hose where you stick your thumb over the end of your hose and you're able to shoot water out of it. What you've done there is you've created a blockage on the end of your hose that converts pressure into velocity. Well, how can pressure be converted into velocity? It's all related to the relationship between pressure and the area that you're trying to work with. So, and this comes down to the laws of thermodynamics. Essentially, the laws of thermodynamics say the system has to stay balanced, i.e. the energy I put into a unit of water moving, just assuming water or gas or whatever's moving through the pipe, any energy I put into that gas has the same energy downstream of that pipe. However, the way in which the energy is measured is that some of the initial push I put into it disappears in friction and turbulence. You don't see it per se, but that energy is being dissipated. And another way to look at it would be like, imagine a bunch of people trying to get through a door. If you widen the door, you're going to be able to get more people through. But you can imagine everybody trying to scram through the door and everybody's pushing and being, kind of non-uniform. Now, if you got everybody to kind of get into a line, they'd get through that door a lot easier. Wouldn't necessarily mean they're getting through at the same speed or at the same rate. However, they're able to get through the door more easily. There's less turbulence and there's less friction. Do you get what I'm saying there? Another way to look at it is this, and this is something I like to conceptualize too, and this helped me with the velocity and pressure idea. Okay, imagine you got a bag of gas, but the bag of gas is full of gas molecules moving around. Replace the gas molecules with baseballs. I got a bag of 60 baseballs. I want to get those 60 baseballs to you in 1 minute. So I got 60 baseballs, and I can do it in one of two ways. I can gently lob that entire bag over to you so it takes a minute for it to land in your lap, or I can shot peen those 60 balls at you a second. Do you get the difference there? One is moved really slowly to accomplish that 60 balls moving over in 1 minute. The same work was done. I moved 60 balls from point A to point B, but I did it in two different velocities. One, I was shot peening those balls. I was picking a ball out of the bag and firing them at you a second. I got all 60 balls to you, but the other one, I just gently lobbed the bag over. That's the concept of pressure and velocity combined into one idea. And that's always helped me in terms of kind of understanding, again, how some of these concepts of pressure and velocity come into fruition and relate to each other. So as an example, I might say, okay, here's a problem I have in a typical day. I have 5 new wells coming online. Each one of the wells does X amount of production. I already have a pipeline system that's generally full of gas per se. It's full at X pressure, but I'm going to try to jam more in it. Well, how do I do that? I mean, the system's full. I have to let something give, right? Something's got to give. So what I'm probably going to do is watch my system pressure up. So now if you want to think of it this way, I've squished more molecules of gas into every cubic foot or every linear foot of pipe that I'm producing now. So maybe things are moving a little slower, but even though they're moving slower, I got that big bag of baseballs coming at you instead of the shot peen, instead of those individual baseballs coming. So I'm doing maybe more over unit time, but it's moving slower. So these are the concepts that I try to use to go and frame all of these ideas like friction, pipe losses, and all of these things that are kind of buttoned up into usually very usable numbers. Like, as I understand it, you guys look at friction in a unit of friction per meter of pipe, right? That's kind of how you guys see those numbers, if I'm not right?
Yeah.
So if you see those numbers that way, that also assumes a couple things about the pipe. It assumes that the pipe wall is the same all across it. Well, is that true? It's true in general. Like, it's not perfect. Like, you're never going to get every molecule to look exactly the same. It's like none of my strands of hair in my head are curled the same way. They all curl a little different, which is why it looks crazy up here. But anyways, outside of that, you can see how, like, you have to generalize some certain things, and you do experiments to go and say, okay, when I push this much water through pipe, how much friction force do I have coming back? What kind of losses do I have at the other end of the pipe? How do I make this mass balance, this equation balance itself based on the laws of thermodynamics saying that things kind of have to stay whole? So is there any other questions coming out of this, guys? Like, I mean, these are concepts, like, I'm not gonna lie, they took a little while for me to understand and get a full grasp of, but it's using these spatial relationships of that ratio of area versus that circumference that is gonna kind of help you realize how things are changing and why, even though there is more pipe wall to contact, your friction per distance is going down as pipe size increases. And that's just a function of how the fluids are flowing through those pipes, the turbulent and frictional forces that govern what is pushing back on you as you're trying to move fluids through those pipes. One thing I was talking to you guys with one of my colleagues here, and it was an interesting concept because I think this kind of says it too, and it's a different way to think about it. Most of the problems that you guys are looking at involve assuming that the fluid is in the pipe and that the pipe is full of fluid. And an interesting concept would be, take your 2-inch garden hose and now keep the volume in the hose the same and put that into a bigger pipe. Well, now, like, the concept becomes, well, now you got a garden hose worth of fluid inside this big pipe. Well, you're only contacting a small portion of that pipe for any of the frictional forces you need to overcome. So that, like, that's another way to just show how, like, space within the pipe would also govern how that flow regime works. Now imagine, in my world, this is what I generally see. I have a pipe that's full of water, gas, and oil, and hydrocarbon liquids, and then gas on the top. So I have 3 different phases of fluids flowing through my pipe at any given point in time. And my job generally at the end of the day is to ensure all of the liquids that are in that pipe are moving alongside of the gas. And you might say to yourself, it's like, well, wouldn't a gas move a lot more easily based on the fact that it's a lot less viscous? Like, gas is, like, the air around this room is obviously less viscous than if I had to put my hand through water, right? I would feel a lot more resistance in water than I would in the air that I feel. There's still resistance in air, and I'll prove that to you with this concept. Think of a straw and think of moisture inside a straw. I could blow through the straw gently and I probably wouldn't get any moisture coming out the end. But then if I really blow through that straw, I can get those water droplets that are in it to move out, and if I want to, spray in the face or do whatever the heck I was looking to do with that moisture coming out the end of the straw. But that's proof that the friction from what I'm blowing out of my mouth, the molecules of material, or basically, you know, the exhale materials, are impinging, they're hitting those water molecules in the straw and moving them. So I can do it gently and they'll just kind of move past them. And that is almost like, think of it like the eddy you just move past that little turbulent spot and got out, versus enough energy there is going to move that droplet. It'll actually put force on the droplet and move it. So that is a gas imparting a force onto a liquid and actually moving it out the end of a straw. So I was talking for about a half an hour, guys. That was a pretty good rant. I definitely appreciate you listening to what I had to say. One, and two, I hope that helped with some of the conceptualization here. But is there any more questions that you guys can think of? Is there anything that's bothering you? Like Mike was saying that sometimes some of the modules do have some mistakes at the end. That can be very frustrating. But I will say that gives you guys an opportunity to work as a group and look at why they might have got the wrong answer. Because I'll tell you, as an engineer, we get the wrong answers sometimes. And when we get the wrong answers, oftentimes that lead to us never getting the wrong answer again. You need to make sure that you're learning from your mistakes. It's not the worst thing in the world. And even having an error at the end of that module might get you guys engaging in more conversation around why they were wrong or what they might have done to get that wrong answer. So, I look at every, I don't call it failure, but every misstep is an opportunity to learn from it, push past, and get to that point of further understanding about what the problem is. And I can even anecdotally tell you about, so we had an erosional failure on one of the pieces of pipe that I worked at up in Northeast BC in 2007. It was a big deal. And this is an interesting concept here, we had economically driven mandate, save money. How do you save money? Well, you buy smaller pipe, etc. You do things that are, I don't want to say you short yourself, but you look for ways to save money, usually involving lesser grade materials, etc. So what ended up happening was we kept drilling better and better wells, but the message about the wells we were getting didn't seem to trickle into our facilities department. And the facilities department at the time were designing facilities based on what they were given. They were given X rate, and they were given X pressures and this volume of X, Y, and Z. And they did the calculations based on the numbers they were given. Well, those numbers kept changing. And then we got to the point where I, sitting in my seat, was saying like, geez, we're running 2-inch gas lines off of these wells. And I'm thinking about, I'm trying to be practical here. I'm like, man, they run 2-inch gas lines for like 40 PSI low volume delivery up in Athabasca to go and, feed fuel gas lines out to, let's say, engines or something. It's like the concept of a 2-inch line being able to handle the amount of gas didn't work for me. So then I went back to the drawing board and I started looking at, what did I look at first? I looked at velocity in that pipe and said, hey, at this flow rate and these pressures, the velocity in this pipe is X. And I know that velocity in this pipe over and above 60 feet a second, just as an example here, is going to cause me erosional concerns, because it's not just gas and water and oil I'm bringing up. I'm bringing up particulate matter. I'm bringing up formation fines, like actual pieces of the reservoir. I'm bringing up the sand they use to fracture the well. All of that stuff is coming up with a liquid. You could imagine, gritty pastes that they might use to paint on a floor, right, for extra grip and whatnot. If you touch that liquid, that paint, there's grit in it. Yeah, you're able to suspend that grit within that viscous fluid. That is exactly like what I was producing out of the wellhead. Now, the other thing we had is we had a couple elbows. You had mentioned elbows and that fluid flow around the elbow. Well, now I had all this sand-laden fluid, so basically like a sand gun or a sandblasting gun. I had the nozzle pointed right at an elbow. That elbow failed in, we figure, somewhere around 15 minutes. It ate through 3.2 millimeters of steel. That literally blew a hole in the pipe that was about yay big. Well, it was, I can't visualize it here on the screen, I'm sorry. But it blew a very nice hole in the ground. There was enough pressure and force coming out of that hole to cut a 4-inch hole in the ground, to move 4-foot hole in the ground. And also there was enough pressure that it was leaking out the pipe, but also still flowing down the pipeline, because there was so much gas, it just needed to move in both directions. It was just wild. Anyways, thankfully, I kind of covered my own rear end by having done a presentation earlier that year on the concerns we had around the potential velocities we would see with these increased rates. And it didn't go anywhere, but I'm not gonna lie, that really did save my rear end when it came time to go and discuss this failure as an entire company. It was a big deal. We had to meet with the town of Dawson Creek because we'd filled a valley full of sour gas. There were residents that were bothered by this. They no longer trusted our designs. They thought that more of these designs could be like that, and they very well could have been, because we were designing for this. It caused us to shut an entire field in, rethink everything, repipe a whole bunch of wells that had already been done. So there's us redoing work And the way I like to look at that, I look at that mistake as a mistake from me maybe not sounding the alarm bell enough, but also think of the amount of wasted materials and efforts from people having to redo all this work again. I mean, if there's one good concept we can take from this whole lecture, it's like, do it once, do it right. You don't want to be redoing things. You don't want to be pulling the speaker out of the roof because it was a bad speaker when you put it in there, just as a crappy analog to the examples we were using earlier. It's like, have that vision of what could be done if it was done as right as it could be. Take pride in your work. That will be a huge thing that you guys are going to see when you get out to the job site. You might recognize that some people aren't doing that. Don't follow their lead. It will not lead you anywhere but bad. Be the best at what you can do. Look for the best people that are out there and shadow them. Learn from them. Ask them questions. I've never heard one stupid question. The only stupid question that comes out of somebody's mouth is the one that didn't get asked. Because sometimes it's not even like, you may even ask the dumb question and you just needed to kind of, oh, right. You needed to ask it to get through it yourself. Just don't be afraid to do that stuff. I personally, my favorite thing is getting a call, and I get calls from the guys out in the field all the time. Actually, we got a bunch of girls out there too. So from the people out in the field, I get calls from them all the time. And the first thing they usually say is, sorry to bug you. And I'm like, this is the most bugging conversation I'm going to have in my day. We're talking about improving our workflow or improving your life a little bit when you come to work every day. I think there's no way that could be a bad conversation. It just generally is going to lead to something better. So if I can leave you with anything today, I encourage you to ask those questions. Touch base and make connections with the people you're going to work with when you get out there. Look for that seasoned guy that's doing something and ask them why they do it that way. There's probably reasons. Don't look for shortcuts. Shortcuts aren't what anybody's asking you to do. Again, I think the shortcuts come from not doing the work. I can use my erosional failure example I just spilled out there. That came from not doing enough communication work. We weren't communicating back to the facilities department what was changing. And how would they know? You can become so big in a company that sometimes you lose sight of what's happening. And again, I will emphasize that you guys are going to be the eyes and ears. You're going to be the boots on the ground that go and make these facilities work. You're going to be what's bolting up A to B. And when you have that extra insight and that extra ability to be like, you know what? We should have gone 4-inch pipe here based on the fact that I think the velocities are going to be too high based on what I see or based on what fluids you're producing. Those concepts will come to you over time and will make you a much more powerful employee and partner, if you want to call it that, in the quest for better, whatever that better might be.
Chosan, you had a question? Yeah, come on up.
So my question is, in a system, right? Like in a line, if you're introducing like an ORIF plate in the middle, so how do you determine if, depends on what you're flowing, has a little particle on it, right? So how do you do the calculation, like for those particles that's going to be attached to the ORIF plate with the friction on the wall of the inside of the pipe?
Okay, so I'll go back and I want to make sure I got your question right. So we're talking about an orifice within a pipe, right?
Yeah.
Is that what we're talking about, an orifice? Okay, so, and everybody knows what an orifice is. So that's just basically a restriction within the pipe. And I think what you're asking then is, how do you calculate the velocity through the orifice, or how does the orifice create friction, or what kind of friction does that create?
So what kind of friction does it create when there's a particle on the fluid flowing through?
Okay, so you've asked a good question. So to solve that equation, like what does the actual orifice impart for a friction component, or what friction component does that add to it? So there's a couple different ways of calculating that, should we need to calculate it. So then the first question you should ask is like, okay, well, what information could I have available to me at any given point in time within the system? So if I know pressure upstream of the orifice and I know pressure downstream of the orifice, and I assume that, again, our laws of conservation of energy are the same, I should be able to use a velocity equation to go and say that like your P1V1, so your pressure and volume on this end, is equal to the pressure and volume on this side. So what's going to happen there is you're going to see a massive reduction in the overall pressure on the downstream side of that orifice. And that pressure reduction is the friction component of what that orifice is doing. So, I mean, that's an easy way to look at it right there, because you're going to be able to see that differential in pressure right away. And then you would have to take that pressure back and do the equation to understand exactly what frictional component that's adding. But that is the answer. Like the pressure upstream and downstream of that orifice is going to give you the frictional factor that that's introducing. Obviously, as the orifice becomes bigger, the frictional factor and the pressure downstream will be a little higher. So you will realize less loss as that orifice becomes bigger and approaches the inside diameter of the pipe. Does that make sense? Does that answer your question? So you need those pressures to go and do that calculation, and then you will be able to find out what frictional component is being introduced by the actual orifice itself.
Okay, one more question, Darcy.
Yeah. Me and Mike there, who's the better music player?
It's a great question. It's Mike. He's pretty good on that guitar if you haven't seen him. So yeah, I just do the singing, so.
Okay, any more questions, folks? Yeah, Kyler's got one here, Darcy.
Fire away.
So, explaining orifices to us, would an orifice create like a Venturi effect inside the pipe? Or
Yes, absolutely. So what's happening? So think of your orifice exactly like that thumb over the end of the hose.
Right.
You've taken. So if you think about it, at the end of the hose, because the water's moving, it has a pressure. Something's pushing that water out, right? And the example of our house, it's like, well, the city water system is pressured. You have now had a way to relieve some of that pressure, and it's coming out the end of your hose. You stick your thumb over the end of that hose, and what you've done is you've basically added an orifice. Like you've created an orifice. You've taken the, what would have been the circumference or just the area, and you've reduced the area by the area that your thumb takes up. So what you've done is you've created a blockage, you've thrown friction into the equation, and then how friction relates to that Venturi effect that you're talking about is in that velocity equation. So assuming that the same amount of water needs to come out of the end of that hose, I've provided a less area to do that, and it has to do it faster. It's the bag of baseballs example I was talking about, right? Again, what was coming out of the end of your hose was that bag of baseballs nice and slow. The minute you put your thumb on it, you made the baseball bag open up and you started shot peening baseballs out there. You're still getting the same amount of baseballs per unit time, but you had to do it faster. Does that make sense? That's what you're doing with that orifice. So, and orifices are important things, right? I'll give you an example. We have inlet separators. So gas and oil will be coming into a facility. I can't compress fluid like actual fluid itself. It's an incompressible fluid. So I do not want that going anywhere near my compressor. I got valves going back and forth that are smushing gas together and sending it out at a higher pressure. I cannot smush fluid. If I go to do that with the piston, it'll just break the piston. The engine will shut in, something will fail. But the point I'm trying to make there is that, you can see how, gas itself can be squished a little bit more. It's the same concept as the fluid, and all of them have to do with that velocity and pressure equation relationship. So you think about that bag of baseballs example, and that's exactly what you're doing when you're doing the hose or the orifice.
Got it.
Does that make sense?
Yeah.
Good.
Perfect. So yeah, when basically the way I like to think of it too, just to simplify it even more, is that if you're losing pressure, the laws of thermodynamics say that it's being converted into something. If you're losing pressure, it's either disappearing in heat, it's disappearing in friction, or it's being turned into velocity.
Oh, one more here.
Yep, fire away.
From the inlet separator you just talked about, right? Because there's a gas, there's a fluid, there's a water, all different kind of shit coming in the inlet separator, right? So like,
yes.
What kind of friction or forces had inside like the inlet separator, because it's compressed with different fluid and gas and substance, sand, whatever.
Absolutely. So, okay, this is what I'm doing with an inlet separator facility. Basically what I'm doing, all I'm doing is messing with velocity. So now what I've done is picture a garden hose into a swimming pool. that garden hose is going to take forever to fill that swimming pool up, right? But what did I do there? I mean, it'll eventually get to the point where the swimming pool fills up, and let's say I've got like a little spout on the other end of the swimming pool. Whatever I'm putting into the pool is going to be coming out the other side, right? Just due to the fact that I'm adding to it. That is, I'm just playing with velocity with that separator. I take a whole bunch of fluids and I let them expand in this space, and I let a fluid level start to build up in my inlet separator. Now, the way in which inlet separator, this is kind of getting into a little bit of a different concept here with respect to what we're talking about in fluid velocity, but you do have a good point, because you can imagine that the fluids in my inlet separator will start to build, and then I hit a level switch, just like the level switch in your toilet. That'll basically trigger a dumping mechanism to open on the bottom of the separator, and that separator then, now I've got, picture a level in the separator and this gas head. I've got a gas pressure on top of it. That's going to push that out. That's going to push that out, whatever outlet I opened. Now, the outlet I opened has flow through it. There's going to be a velocity in that flow. So I need to manage that accordingly. There's where your orifice plates come into play too, right? Because I might have all this gas pressure pushing fluid out that is moving too fast for what I would like. I could put an orifice in there and potentially slow that down a little bit, so that I can move fluid around an elbow and then it hits an orifice and it just backs it up. It just basically makes that fluid moving out of the separator move slower. Downstream of the orifice, it'll be moving faster. But that's just the relationship that the orifice adds in there. But with respect to how that inlet separator works, also, you know, generally speaking, I've got my fluids coming in and the gas will come out the top of that separator, assuming I'm looking to degas the fluid. Again, I want to pull that gas off of the inlet separator and put it through compression so I can get it out to sales. However, those liquids and will build in the separator and do need to be dumped periodically. So the rate at which those liquids are coming into the facility and the rate at which they need to dump to clear them is all something you need to take into account when you're designing the facility itself, i.e. how big an inlet pipe do I need, what size of inlet separator do I need, and how fast do I need to be able to take those liquids that build up in the separator out of it so that I can get them to sales as well. Does that make sense? Awesome.